Okay, let's start. Okay, good morning. I got your assignments here, so I'm going to return those to you guys. Okay, and the solutions posted, so you can mark going over the solution. You can mark yourself, right? Yeah. Did anybody drop the assignments over there? Yeah. Oh, you did. Okay. Okay, so I haven't picked those up yet. I need to get a key for that. Yeah. All right, that's fine. I'll give back to you next time.
When do you want more what we got on? Like when do you want us to tell you?
Oh, anytime before the final exam.
Right.
Yeah. So no hurry. Okay. Okay, so let's continue from our previous lecture. Okay. There's one little thing we didn't finish from previous lecture. Okay. In previous lecture, we had a a topic on discretization of a continuous state space model. Right? So basically, if you have a continuous system, yeah, sorry, I use F, right? If we have a continuous system, and then we can discretize this one using zero-order Hall equivalent. So we end up with a discretized state space equation. The relationship between the system matrix A, B, C, D, and F, G, C, D, basically C and D are not changing, it's just A and B changed. A is equal to e to the power of F capital T, T is sampling time, and B equal to the integral 0 to T, okay. What was the formula again? E to the power of, e to the power F lambda d lambda multiplied by g. Okay, so that's AB here, right? Yeah. To calculate this e to the power ft, okay, what we do is we calculate e to the power ft first, okay, and that's Laplace inverse, okay, si minus f, okay, to the power -1 of this. Yeah, today maybe I'll show you another one of the approach of calculating e to the power ft here. Okay, yeah. But that's basically what we covered in the previous lecture. We had example, basically going over the process, right? Yeah. There's one more topic at here just to finish that. So remember the origin of this whole thing here. Okay, so this is a continuous system. Origin is always a continuous system. Right? Your continuous system origin probably started with the ordinary differential equation. And from ordinary differential equation to a Laplace transfer function, right? So the transfer function is really sometimes what we want instead of the state space equation. So if origin is the same thing, then the transfer function should be the same thing, basically describing the system as the state space equation here. Okay? So the question here is, what will be this pulse transfer function? Okay, what will be the pulse transfer function based on this discrete state space equation at here, right? So it's like this kind of relationship, right? If I have a h of s representing the transfer function of the continuous system, then h of s can give us a continuous state space model, right? Continuous state space model. And h of its continuous state space also can give us a discrete state space model. And h of s can give us a zero order Hall, maybe h of z here, right? So this is zero order hold and zero order hold, okay? And then these two, right, basically are the pair here, okay? Yeah. So now the question here is, I have the discrete, okay, state space model here. Oh, I call it T here, state space. State space. This is a discrete state space model, and what will be the Pulse transfer function here? Okay. So of course you can argue, if you want a Pulse transfer function, I can always try to derive Pulse transfer function from original h of s, right? Yes, of course. Okay. But let's look at from here to here. So this is your discrete state space model here, right? This is discrete space model. So what we do is, okay, mainly based on this one here, let's take a z transform, taking z transform of both sides of the equation at here, okay? Taking z transform. Now, when you take a z transform, okay, technically, okay, this x of k plus 1 at here, okay, technically you should have capital X of z and small z at here. So there's a vector sign at here minus, okay, z x of 0. Okay, so that's the z transform x of k plus 1. And the other side is capital X of z, right, x of k's z transform. There's a there. Okay, plus b and u of z, right, u of z. So since we're dealing with a single input, single output here system, I'm going to get rid of the vector signs for temporary. Okay, yeah. And the other side, the other equation, y of z will be c x of z plus d and u of z. Okay. Okay, so this is basically the taking z transform. This is what we have. And what we're looking for is a transfer function, right? It's transfer function. So when you're looking for transfer function, one of the assumptions is you always set the initial condition to 0. Okay. So basically, you can get rid of this term temporarily, okay, but not on some other situation. Only when you are trying to look for transfer function. Okay, yeah. So if this is the case here, then looking at the first equation at here, looking at the first equation, then what we have is z, okay, x of z, okay, minus a x of z equal to b and u of z, right? This is the first equation. Taking out the common factor x of z, okay, taking out the common factor x of z. Now you got to be careful. When you're taking out the common factor x of z, this is not scalar here. Okay, so order matters, right? So we don't put this one in the front and then the other one at the back there, right? Yeah. So here's a. So this is z, but this is not a z anymore. It's going to be zi. Okay, so z multiplied by a unity matrix. Okay, so that we can do this subtraction at here. So that equal to b u of z. So then your x of z, okay, equal to the inverse of this multiplied by this one here. Okay. So that's your x of z in terms of x of z and u of z here. But your Pulse transfer function is the transfer function between y and u. So what we do, we substitute this term over here. Okay. So substitute it here. Then we get y of z, right, equal to c zi minus a inverse b and u of z, okay, plus d u of z. Okay, yeah. So it's nicely that both term has a u of z here. So taking out the u of z and get the ratio, okay, which is the Pulse transfer function, right? So this is the Pulse transfer function, okay, which is what? Which is c zi minus a inverse b plus d. Okay, so this is the Pulse transfer function from discrete state space model. right? Yeah. And this post-trans function, this one, right? It's supposed to be, okay, the same as, okay, this approach at here, right? Same results from h of s to h of z. Okay? So from here to here, from here to here, you should have the same results. Okay. So let's say if this is representing, this is h of z here. Okay, it's representing h of z. H of z is the zero order Hall equivalent discretized trans function. And technically speaking, right, this is the same thing, okay, as what? As a zero order Hall of this. Okay, so that should be the same thing. Was that good? Yeah. So, in the previous lecture, we had an example, right? That example is, okay, that example. So you can take a look at that. Basically, that in that example, h of s equal to this. Okay, in that example, h of x equal to this. We did a discretization. Basically, we obtained a, b, c, d. And you can look at the lecture notes, you know, basically this is all matrix here, algebra, linear algebra, multiplications, inverse, so it's not too much, nothing new at here. So you can simply substitute a, b, c, d at here, and then you can derive y of z over u of z, right? You can do a comparison here if you do a z transform for a zero order Hall equivalent to block there, okay? And then these two results should be the same here. Alright? Yeah. So take a look at that part of the lecture notes as a little exercise there. Okay? Yeah. Any questions? Okay. Okay. So now let's get on to a new topic, which is similarity transformation and a state transition matrix. So those topics here, you know, basically, if you don't learn control, okay, it's pretty much a linear algebra topic here. Okay, yeah. So it's kind of standalone things here, but we use them. We use those knowledge in terms of a better understanding of our control system. Okay. So first of all, let's look at the similarity transformation. And let's see what does that mean here. Okay, what does that mean? So similarity transformation in general, at the top of the definition is this. Okay, definition is this. Given, let's say, a matrix is, okay, let's say A and B. Okay, so in general A and B. Okay, not the A and B over there. Okay, so giving a matrices A and B. Let's say they are real and they are n by n matrices. Okay, yeah. Then let's see. Then for let's say for a non-singular, okay, for a non-singular, okay, matrix P, okay, for a non-singular matrix P, if this B equal to this, okay, if B equal to this, then what we see is A and B and B and A, or A and B, doesn't matter. So we see B and A, or let's say B is similar to A. Okay, so we see B is similar to A. Okay, so that's similarity. Now, in terms of notation wise, so what we do is we use this B tilde A, okay, to represent this similarity at here. Similarity. Okay, that's called the similarity concept. So there are a couple of properties for similarity, right? Number one is called reflexive property. So reflexive basically means any matrices, any n by n matrices, okay, they are similar to themselves. Okay, they're similar to themselves. And why is that? Because you see, you can always find a relationship of this, right? You can always use identity matrix. Identity matrix inverse itself, and then by A by I, so right, so that satisfies this condition in here, similar. Okay, and secondly, symmetric property. Symmetric property basically saying is A similar to B, okay, implies B similar to A. Okay, so implies B similar to A. So why is that? See, if B equal to this, okay, if B equal to this, and let's take a very simple linear algebra operation in here. If B equal to this, then I'm gonna multiply P at here and P over here, right? So this P inverse becomes what? Unity matrix. And then we can multiply P inverse here, P inverse here. So basically that gives us A equal to PB P inverse. You see that? Right? So this A equal to PB P inverse, that's actually in the same format of this one here. Basically, see, here it says there exists a matrix P such that B equal to this, right? P inverse AP. And this is not P inverse, but this is basically P inverse inverse, right? Yeah, so it's same format as the definition. So A is similar to B, meaning B is similar to A. Yeah, as long as they maintain this relationship. Okay? Yeah. The last one is transitive. Transitive. So transitive meaning if A is similar to B and B is similar to C, okay, so then that means A is similar to C. Okay, C is similar to C. Okay, yeah. So it's actually quite easy to derive. Let's say if B equal to P inverse AP, so that means A is similar to to B. B is similar to C, so then C may be equal to this, right? Maybe equal to this. Then I can substitute this B over here, right? Over here. So that means this is Q inverse P inverse A P Q. Okay? Yeah. And this Q inverse P inverse, that equal to PQ inverse. Okay? Yeah. So basically the linear algebra property PQ inverse equal to Q inverse P inverse. Right? Yeah. So this is basically meaning C is similar to A or A is similar to C. Okay. So this is a similarity transformation, all right? The similarity transformation. So why this is important to us is because, okay, if you remember in the lecture that when we're deriving for the state space model from a Z transfer function, what are the two different type of state space model we end up with? What are the two typical ones we end up with? You have a Z-trans function. You know, we draw a similar simulation diagram, and we define ourselves certain state variables based on the simulation diagram, and we end up ourselves with some state space model, right? What are the two very important ones we discussed about? Anybody? No? There are two canonical forms. One is called, when I say canonical form, then you should remember that, right? Where are they? One is called control canonical, and that is what? Right? Form. So basically, what's the control canonical, observable canonical? See, this is basically the format or the formality for the system matrix, the A. This one here, right? Remember this is for this A here. They look different, right? Basically, when you derive the state space model, number one rule you need to understand is there are infinite number of solutions of a state space model for the same system. Okay, they're infinite. If there's infinite, basically means there are infinite number of matrix A at here for the same system. Okay, and there are a couple of them of particular interest to us. One is this control canonical, the other is this observable canonical. Actually, there's another one, okay, called diagonal form. Okay, another one called diagonal form. Okay, so those are particular interest. So now the question here is, if the A can take up this many different formats, okay, maybe I'll open up the lecture here. So when we draw this diagram, if you recall this diagram, what format did we end up with? This is called control canonical form, right? Control canonical form. You see, this is a matrix A here, right? This is matrix A. Okay. And if you take inverse of this matrix A, we get this, which is the observable canonical form. Okay. Yeah. Now there are different other ones there. So in the lecture notes, I didn't really go over all the details, but in the end, there are a couple of examples here. This example, so let's say this is your Z-transfer function, right? This is your Z-transfer function. So now we're trying to derive state space model, and we have different approaches. If we draw this kind of a simulation diagram, we end up with a control canonical format. Okay. If you draw this kind of format here, you end up with a diagonal. You see that? Oh, sorry, this is not diagonal. This is actually not diagonal. This is a cascaded format here. But if you do this, if you do a partial fraction expansion, okay, this is basically two things adding each other. It's like in parallel. And you draw your simulation diagram in parallel. Okay, in parallel here, we end up with a diagonal at here. Okay, we end up with diagonal. The elements on diagonal elements on the diagonal location is what? Is the poles of the system. Okay, so but all of this one here and this one plus the other ones, they all represent the same system, right? They all represent the system. Okay, yeah. So now the question here is, if they all represent the system, then all of these different A matrices, they can be converted to each other, okay, from any other form using this similarity transformation. Okay, so basically the language, the conclusion here is so all forms of matrix A, okay, so all forms of matrix A can be converted from any other form by similarity transformation. Okay, yeah. So when we're saying all forms, right? When you see the when you see the forms added here, whatever referring to, basically they can be control canonical form, they can be the observable canonical form, and they can be a diagonal form. Right? So that's what it means that here. Or they can be any general matrix formats without the name. All right? Yeah. Okay. So of course the whole question here is, okay, so basically your immediate question will be, okay, given A, okay, now if I want, right, let's say given A from a certain discrete state space model, and then you probably say, okay, how do I convert this A to the diagonal format? How do I convert this A to a control canonical format? And how do I control this A to observable canonical format, right? Yeah. So that's actually what we're going to deal with, all right? Yeah. So how to convert to desired format or form? Okay, yeah. So keep that as a question mark. Okay, so let's look at this general idea here. Okay, let's do a general idea here. Let me rewrite this discrete state space model right here. Okay, it's a bit far on the top there. Okay, so here's this discrete state space model. Okay, now what I'm trying to do now is to do this transformation now. Here's what happens here. Let's do this. I'm gonna apply this now. We're gonna let this WK, okay, equal to P inverse X of K. Okay, so we're gonna let this WK equal to P inverse X of K. So what is P? And P is the arbitrary n by n non-singular matrix, okay, or invertible basically. Okay? It has this inverse. So at this time, I don't know what the P is, but I can pick any P as a non-singular invertible basically matrix n by n. Okay? So WK equal to this. What's X of K? X of K's meaning is the state variable of the system, right? If I do this, and then basically I have a transformation from your original state variable to a new set of a state variable here. You see that, right? So this is basically a new set of state variables. Okay, it's a new set of state variables. Okay. So WK equal to this, meaning X of K equal to P W of K. Okay. Now let's substitute this change transformation back into this discrete space model. So x of k equal to this, then x of k plus 1 must be pwk plus 1, right? Yeah. So pwk plus 1. Okay. This is a pwk plus b u of k. All right, and then the y of k equal to c at p wk d uk. Okay. So coming from here, this is p at here, and I multiply p inverse by both sides. Okay. Then the first equation basically becomes wk plus 1 equal to p inverse ap wk plus p inverse b uk. Okay. So now you have, if you look at these two equations here, now you have a brand new state space equation, right? State space model. Previously, your matrix here is A, that's for X. Right now it's W, and this is a new system matrix, P inverse AP. So isn't that basically the similarity transform, right? According to the definition, right? Yeah. Okay. So let's see if I call this AW here. Okay, and this call it BW. And then this CP at here is CW. So D didn't change, right? D is still the same thing. Okay. So DW, same thing. So basically AW is the key here. AW is P inverse AP. Okay. Alright. So now you have this brand new state space equation. Well, we said it's a brand new. However, you still have to bear in mind it's not really brand new. It describes the same system. Okay, it's not nothing new. You know, basically, it still describes the system. If this one describes the same system as this one in here, then there is this thing here. What describes the dynamics of the system? You learn in control system. What gives you the dynamics of the system? That's you have transfer function, right? What determines the dynamics of the system? Or what determines the characteristics of the system?
Impulse response.
Impulse response, okay. And what else? You say impulse response, still response, right?
Yeah.
But what characteristics from the system, what properties from the system determines the characteristic system? Zeros in the pose, exactly, right? Yeah, more important is the pose there. Okay, so the location of the pose determines your dynamics of system. Then, when you see pose, you're talking about transfer function. Actually, when you see this, when you look at the state space model, you still have pose, but we don't call it pose anymore. We call it eigenvalues. Okay, we call it eigenvalues. So eigenvalue of this matrix A will be the pose of your transfer function. All right. So let's say maybe I'll show you it here. Look at this one here, right? What's this? This is a Z transfer function, isn't it, right? So what's on the denominator here? You look at this. If you look at this one here, what's on the denominator? Which one? This?
A.
Yeah. No, not A. Zi minus A, right? Yeah, Zi minus A here. That's basically on the denominator. But yeah, technically, if it's scalar, this is going to be on the denominator, right? So the pose of this one is actually going to be the eigenvalue of this. Basically, it's going to be the eigenvalue. What's eigenvalue? I think you learn. If given a matrix A, what's eigenvalue? How do you get the eigenvalue? Lambda I minus A, and then you set a determinant equal to 0. The solution of the lambda is the eigenvalue, right? Yeah. So the eigenvalue here basically the poles of your original system. Okay. Yeah. Okay, I'll give you original system here. Okay. Now, usually when we say posal system, what we don't use lambda. We said we use z because we're dealing with discrete, right? So we can call zi minus a determinant equal to 0. Okay. Yeah. So that a is for the initial set of discrete model, right here. But now you have the transformation, which is AW now. Then technically speaking, if this state space model describes the same thing as previous one, then the eigenvalue or the poles of this system should be the same as what? As this guy here. Does that make sense? Right? So basically, then this Zi minus AW equal to 0 should have the same eigenvalue as this one. Okay, or should produce the same eigenvalue. Okay, yeah. So let's see if that makes sense or not, right? So let's do this, right? Let's do this. So what's AW? AW is P inverse A P. Okay. Yeah, this is Zi minus AW. Okay. Yeah. Now we make a little modification at here. Okay, we make a little linear algebra modification. Modification meaning we don't change anything, but it's basically equivalent operation at here. Okay, equivalent operation. So look at this I there, right? The I is the identity matrix. If I multiply this P inverse P like this, sorry. Okay, so basically I changed I to P inverse IP. I'm not changing anything, right? I'm not changing anything because P inverse P is still what? Identity matrix, all right? So minus P inverse AP. Is that okay? Yeah. So I'm not changing it, but it's just rewriting it, introduce this here for ease of operation. So then you see this guy here, P inverse here, P inverse here, P here, P here, all right? So that actually can be written as this. So if P is a scalar, then it's quite easy to take out the common things, right? P is a matrix, so it has to be taken out like this. Was that okay? From here to here? Yeah? Yeah. Now remember P is a constant, right? P is a constant. P inverse is also constant. So this whole thing equal to 0, you can't set a constant to 0. So which means, if this whole thing equal to 0, which means what? Right, which means this. So that basically easily tells us the process of finding eigenvalue of AW is the same as finding the eigenvalue of A. So basically, you're not changing the system, right? They have the same eigenvalue or the same poles. All right? Yeah. So that's similarity transformation. So you can basically do any similarity transformation, right, without worrying about am I changing the system or not, right? Yeah. So that's okay. And as a matter of fact, the commons here, the determinant of this, okay, is the same as the determinant of this. Okay, there's an easy proof in the lecture, so take a look at that. All right, look at that. And also the trace of this AW is the same as the trace of this A at here. So what is a trace? Trace is basically the addition of all the diagonal elements. Okay, that's trace. Okay. Yeah. Okay. Okay. So I'll skip one example here. Okay, just kind of to verify, giving A, B, and giving a P, and kind of to verify this thing here. Okay. Yeah, you know what? Maybe I'll just write it here. It's not a big deal. Let's say, suppose that I have a matrix A, which is 0.810, 0.9, okay, and B is 0.1, okay, for the discrete state space model. If you pick a P matrix, okay, if you pick a P matrix as this, so P is in by 2 by 2, and it's invertible, right? Yeah. Then the AW is P inverse AP. Okay. So you do a simple linear algebra matrix multiplication process right here. So you're gonna put this here. Okay, you're gonna put this. Now, then the question is, what's the eigenvalue of A and what is the eigenvalue of AW, right? Yeah, I think you need to have this little simple scales for simple matrix at least 2 by 2, right? So how do you get eigenvalue? It's basically the way I just said it there. So what do? You basically lambda I minus A, okay, set equal to 0 like this. So what do? Lambda I meaning it's lambda 0, 0, lambda right here, minus A minus 0.810, 0.9 like this, okay, and then determinant, okay. So what that means is basically lambda minus 0.8 here, negative 1 here, 0 here, lambda minus 0.9 here, equal to 0. So solve the determinant with this. And what's this determinant? This determinant is minus 0.8 minus 0.9, right, equal to 0. So this multiply this minus this multiply this, and this is 0. So this multiply this minus 0. So that's this guy here, right? Yeah. So apparently the solution of this lambda is 0.8, 0.9, right? Yeah. So that's the eigenvalue of the system or the poles of the system. Yeah. So then you can do similar stuff for the AW to check if AW give you 0.8 and 0.9, right? So of course this is doesn't look as beautiful as this matrix, okay? But I'll try to. You can try to use the MATLAB EIG, okay, to verify the results right here, okay, to verify the results. Okay. So play with this EIG command there, okay? Yeah. EIG not only give you this eigenvalue, but also give you the eigenvector. So which is what we're gonna talk about next. All good? All right. So now let's go into specific here. Okay, go into specific. So now we understand. Giving a system matrix A, I can convert it into any form I want by applying a suitable P matrix, right? Yeah. Now, what are the most interested form for the matrix A? So we mentioned 3, right? One is control canonical, observable canonical, and diagonal. Okay, so you'll see why diagonal is very useful one. Okay, and of course diagonal is used because it's so simple, right? Looks same because everything everywhere else is 0. So then this is basically the next one here. I'm gonna diagonalize, okay, matrix A. Okay, diagonalize matrix A. Right, since the diagonal form of this A is particular interest, let's see how do I diagonalize this matrix A. Okay, through the similarity transformation. Okay, so to diagonalize matrix A, so we have to come up with a certain assumptions first. So the idea is not all matrix A can be diagonalized, unfortunately. All right? Yeah. So the theorem basically here is, okay, if A has, so let's say A is n by n matrix, right? Okay. If A has n distinct eigenvalues, then A is diagonalizable. Okay? Yeah. So if A has n distinct eigenvalues, A is diagonalizable. So if A is 2 by 2 matrix and A happen to have a 2 distinct, okay, eigenvalues, okay, and it's diagonalizable. Okay. And if A has n distinct eigenvalues, okay, is diagonalizable. Basically, this implies, okay, this implies there are n number linearly independent eigenvectors. Okay. I'll explain what eigenvectors shortly here. Okay, explain what it is. Okay, so this basically brings us to the next one here. So what's eigenvalue? What's the eigenvector? What's the relationship here, right? So let's suppose that for A, okay, assume that A has Zi and I equal to 1, 2, up to n, okay, distinct, okay, poles or eigenvalues. Okay. Yeah. Then eigenvector is what? So the A multiplied by this Pi equal to Zi and Pi. So Pi is eigenvector. With respect to this Zi. Right, that's eigenvector. Was that okay? Right? So I think in many other courses you probably have touched upon eigenvector. Now the way to understand eigenvector, basically it's a vector, right? Vector representing what? Directions, right? Directions. Okay. So let's see if Zi is a real number. Okay. Let's see if Zi is a real. Okay. Of course, it could be complex, but to explain this next one, we need to assume it's a real. If it's a real here, then what does this expression mean at here? So you have A multiplied by a vector equal to a constant multiplied by the same vector, right? Yeah. So basically, if I in the 3D space, if this is my Pi at here, okay, this is a Pi, this is a vector, right? Yeah. Then when you multiply this vector with a constant, what does it do? The constant, does the constant change? Pardon me. Yeah, go ahead. Exactly, just make it longer or shorter, right? So it only scales this vector. So basically you only have a scaled portion here. This is a Zi here, right? Yeah. Okay. Yeah. And then this guy equal to the other side, A multiplied by Pi. So now this basically brings a question here. Given an A matrix, an arbitrary n by n matrix, right? This matrix is actually, any matrix is a transformation matrix, right? You know, when you learn the basic stuff there, when you say A by X equal to B, right? So what do? We generally do is, oh, I'm going to solve for x, right? I'm going to solve for x there, right? That's what we learned in the first one here. But really what this does is, when you multiply a with x, see x is a vector, right? You end up with what? We end up with a new vector, b. You see that, right? Yeah. So let's see, if x is over here, you end up with a new vector, b, right? After multiplying this a at here. So a is a transform. It's a mapping. You map this x to b. Okay, that's the general functionality of a matrix A. Okay. But now the special thing is, when you apply the mapping A or transform to the vector pi, you know, it doesn't transform it to anywhere else. It only transform it. Actually, it's actually not going to change its direction. It only change what? Its scale. So that's the eigenvector and eigenvalue relationship, what this means right here, right? Geometrically, okay? Yeah. Okay. So remember, this is a vector, right? So this pi is a vector. So basically, in 3D space or whatever, so there is a whole bunch of values probably right here. Okay, depends on the dimension. Right? Yeah. Now we're talking about A has n distinct eigenvalues right here. Then basically what it means is I also have n number of eigenvectors corresponding to each eigenvalue, right? So, and I have this implication right here. When you have n distinct eigenvalue, there are n linearly independent eigenvectors. Okay, so I'll write it here. So basically, if I denote a capital P, which is this, P1, P2, and Pn at here. Okay, so P1, P2, Pn are the eigenvectors for each eigenvalue. Okay, yeah. So if you look at the way I write it here, okay, if you look at the way I write it here, P1 is a vector, basically it's a vector here, right? So what's the size of the vector? It's n by 1. Okay, if the matrix A is n by n, then this is n by 1. So each one of this guy here is a n by 1 vector. Okay, this is n by 1, this is n by 1, this is n by 1. So what will be the size of the P at here? It will be what? Exactly, right? It will be n by n. Okay? Yeah. So the P basically, this is a vector here. You know, if I have some dotted here, so that means it's not just quantity, scalar quantity, it's a vector at each column, right? Each column. So now you understand that is all of them are linearly independent. So what's linearly independent? You know, I think you first come across this concept in 246. Linear independent basically means they don't depend on each other, right? So let's say, for example, I have a 1, 2, 3. This is one column here, right? Maybe this is P1, okay? And I have another column, maybe it's 3, 7, 8. Okay? Yeah. And maybe I have another column 4, 1, 5. Okay? So you look at the 3 columns here. Can you find a scalar relationship or any connections between the 3 columns? Basically, you can't, right? You can't. So in other words, you can use K1 P1 plus K2 P2 plus K3 P3. If you set it equal to 0, the only solution to make this guy equal to 0 is what? Exactly. It's this guy. This is the only solution. If this is the only solution, then this means the three columns vector here are linearly independent. Okay, are linearly independent. Okay, yeah. So if these eigenvectors are linearly independent, okay, if linearly independent, then the P matrix is guaranteed to have, okay, not diagonal. The P matrix guaranteed to be able to inverse. Right. Yeah. So that means P is non-singular. Okay, non-singular. So that's good. P is non-singular. I can use this P in the similarity transformation, right? The similarity transformation. Yeah. So if I do this, P inverse AP, if I use this P at here to do this similarity transformation, I'm gonna get a new matrix AW, right? AW. Okay. And you will see that by doing this, by this choice of P, we get a new matrix, and new matrix is a diagonal matrix. Okay. The new matrix, diagonal matrix. Is that okay? Yeah. So I have a short proof in the lecture notes, so you can take a look at that. Okay. It's quite easy. There's only 2 lines of proof actually. Right. Yeah. So this is actually tells you how do I obtain a diagonal form matrix A. Okay. Number 1, you have to see what kind of eigenvalues does it have. If you have an indistinct number of eigenvalues, then you can diagonalize this matrix A. All right. How do you diagonalize? You basically first you have to find all the eigenvectors. Then you form your matrix P by using the eigenvectors here. Then apply the P in the similarity transformation. You'll get this matrix A. All right? Yeah. So now this probably brings the question down. This is actually more a linear algebra thing here. So the natural question is, what if A doesn't have indistinct eigenvalues? What if A has, let's say n is n by n, but A has only n by 1 eigenvalues? So which means what? Which means there's one eigenvalue actually repeated how many times? 10 times. No.
N times.
Huh?
N.
N times. No. See, A is n by n. And you have only n minus 1 eigenvalues. So that means there's one eigenvalue repeated twice. Right? So basically, you could have a situation that certain eigenvalue repeating itself. Is that possible? Have we ever seen a Pauli's transform function with z minus 0.5 to the power 2, right? Yeah, that's absolutely right. Absolutely. So if that's the case, then you gotta be careful. So basically, if A, there's a conclusion here. It's not very conclusive. If A has repeated eigenvalues, okay, if A has repeated eigenvalues, it doesn't mean that A cannot be diagonalizable. Okay, so A still could be diagonalizable. Okay. So in that particular case, what you need to look at is, for that repeated eigenvalue, let's say if lambda I repeated by, okay, repeated let's say 2 times. Okay, let's see. Then what you need to do is you need to look at the eigenvector corresponding to the lambda I. How many eigenvectors correspond to lambda I? There is a possibility that for one eigenvalue, there are, let's say this is repeated twice, right? There are 2 eigenvectors associated with lambda I, and the 2 eigenvectors are still linearly independent. Okay, so linear algebra, that's possible, right? Yeah. If that's the case, then you still have n linearly independent eigenvectors. Is that okay? Yeah. So basically the whole story boils down to, if A matrix A has n number of linearly independent eigenvectors, then it's guaranteed to be diagonalizable. Okay? Yeah. Okay, so we're not going too much of this but I think in our case, we'll focus on this simplest case here. Okay, usually I'll give you matrix A with indistinct eigenvalues, so it will be diagonalizable, right? Yeah. Any questions so far? Are good? All right. Okay, so yeah, so I want you to take a look at one of the example, MATLAB example in the lecture notes, okay? So just try it out yourself. So try out the commands. Okay. Yeah. All right. So now let's get on to another topic, okay? Yeah, you know what? I'll give you one A matrix here. Let you try this one here. So try this A matrix. Okay. So here's a matrix. I want you to use MATLAB to calculate the eigenvalue of A. Okay, let's see what does it give you. All right. Or you can also use hand calculation to try this eigenvalue A, right? And so try this and try to obtain. Okay, try to obtain the eigenvectors. Okay, try to obtain the eigenvectors. So basically, the A matrix here, I can tell you, the eigenvalue one is 1, the other is 3, and the 1 here is repeated twice. Okay, it's repeated twice. So there is eigenvector associated with the lambda, and what will be the eigenvector associated with the lambda equal to 1? Okay, and are they linearly independent? If they are, can you form the matrix P by using the 3 eigenvectors? Once you form the P, can you use the P here? See what does that give you, right? Does that give us this diagonal matrix? All right, so try it out. Okay, so last topic, okay, is the state transition matrix. Okay. Yeah, what we're dealing with mostly is kind of linear algebra concept here. Okay, linear algebra. Yeah. But they're not too bad. Okay, so we're gonna basically looking at this discrete state space model. Okay, let's look at this state space model here. As a matter of fact, the title state transition matrix. Okay, you can also see as what we're trying to look at is we're going to look at the solution of this discrete state equation. Okay, so we're looking at the solution of discrete state equation. In previous lecture, when we are discretizing the continuous state model, actually we did a process trying to obtain the solution for the continuous state space model, right? Yeah. When we're obtaining the solution over there, we had a state transition matrix. If you remember that, what do we call that again? This guy here, right? Yeah, that's the state transition matrix for the continuous one. Okay, so basically, what will be the state transition matrix for the discrete ones? So we do an iterative process at here. So x1, if you put this one here, x1 equal to what? ax0 equal to b u0, right? Yeah. And x2 is ax1 plus bu1. Okay. And ax1, you plug this x1 into here, so that's a square x0, right? A square x0 plus ab u of 0 plus b u of 1. Okay, so that's sort of iterative process. If you do a programming, right? If you do a C programming and trying to solve this one here, how do you do the program? You're going to do a for loop, right? You're going to do a for loop basically. And the first, starting from 0, okay, then you do a loop until the numbers that you want. This is what happens here, right? So, sort of a embedded loop here. So if you keep going up to k at here, okay, up to k. So if you watch carefully there, okay, this is a square here, 2 is for 2, so that'll be a to the power of k, x of 0, right? It'll be this. Okay. And there are a whole bunch of other terms, okay, whole bunch of other terms in the back there. Okay, you can, pack them all together into this summation in here. Okay, into this summation here. It can easily verify if this makes sense or not. For example, if you set j equal to 0, right? Set j equal to 0, and if you set k equal to 2, so 2 minus 1. If you set k equal to 2, so set equal to 2, basically there are two terms. One is j equal to 0, and the other one is j equal to 1, right? J equal to 1. So you'll get this one here. Okay, you get this. Okay, so the key at here is, okay, so basically this is kind of your solution here, right? This is kind of your solution. If we define this one here as this phi of k, okay, that's phi of k here, like this. Yeah, and temporarily, let's suppose that I don't have any input to the system. Okay, so the system basically is behaving according to its initial conditions, right? Yeah, so then it'll be just this guy here, right? It'll be just this guy. Okay? Yeah. Okay, so basically phi k equal to ak here. Okay, phi k equal to ak. Yeah. So the phi k, this guy here, this is called state transition matrix. State transition matrix. Why is it called a state transition? Because this is a transition from which state? From state at k equal to 0 to where? To the k moment, right? That's called transition here. Okay, so then the next question here is, if I'm looking at a to the power of k, and let's see, you're looking for, so what's the state value at the k equal to 2000? So then you say, oh, a to the power 2000. So we're going to just multiply the a by 2000 times, right? Yeah, so that's how you calculate. But then that's kind of too difficult to calculate, right? Yeah. So we need a shorter or shortcut here to do the calculation. So there are two kind of shortcuts here, okay? There are two kind of shortcuts. One shortcut is to make use of Z transform. Let's say assume that u of k equal to 0. Okay, so no input, okay, no input. If I take a Z transform, both sides here, no U anymore, okay? Just take a Z transform both sides. So what do we get? We get Z x of Z minus Z x of 0 equal to capital X of Z, right? Equal to this. And that basically brings us x of Z equal to Zi minus, there's A here, Zi minus A, okay, sorry, yeah, so maybe I'll write one more step in here, yeah, maybe I'll write one more step here, right, equal to this, okay, so then you invert this guy here, that gives us x of Z equal to Zi, sorry, yeah, so you can take the Z in the front there, Zi minus A inverse x of 0. X of 0, right? Yeah. And what's x of Z? The inverse of x of Z give us what? X of k, right? We've got a vector sign here. X of k. So basically means x of k representing this whole bunch right here. And what's x of k? X of k is over here. So you look at the coefficient, this is x of 0, this is x of 0. So that basically means what? That basically means that phi k, which is a to the power of k, is basically the inverse Z transform of this Z, Zi minus A inverse at here. Okay, so that's when we are finding, okay, this a to the power of k. Okay, that's when we find a to the power of k. Was that okay? So what's the other way? So the other way is what we have just talked about. How about if I transform the A into a diagonal format? Okay, into diagonal format. So let's say, suppose that A is diagonalizable, of course, right? So suppose that AW equal to P inverse AP, okay, is diagonal. Okay, suppose this is this. So AW is diagonal. What are the elements on the diagonal of this matrix AW? Poles, right? Yeah. And then that means A coming back to the AW must be, make sense? Right? Must be this. Okay? Yeah. So, what are we computing again? We're computing what? A to the power of k. So, now A to the power of k, which means we're going to multiply them how many times? K times, right? Yeah. But if you look carefully here, when you do the multiplication here, look at this right here. What's the P inverse P? It's 1, right? It's identity matrix. So the other one, P inverse P, is also identity matrix. So the two adjacent P inverse P is always cancel each other. So that means I have only this P and the other P inverse left, this P inverse left. In the middle, it's the AW to the power of k, right? And what is AW? AW is diagonal, and AW is this, right? It's this. The k power of this diagonal there's nothing more simpler than that one, so which is what? Okay? Yeah. So this is another way of computing a to the power of k. So this is easy to compute. And p, how do I get the p again? I basically try to obtain the p based on the eigenvectors of this a at here, right? Yeah. And p basically will be a constant matrix. Then multiply by this one, and you can get what you want. All right? Yeah. Is that okay? So let me give you a quick example here, but I won't be able to finish the example now. Let's say a is 0, 1, -2, -3. So I want you to use the two approaches that are here to find this a to the power of k. Okay, to find this a to the power of k. So first approach is to find a to the power of k by using this one here, and the second approach to use this one here. Okay, to use this. Yeah. And you can see which one is simpler. Okay, and you can try MATLAB to do this in both cases. But when you use MATLAB, okay, there's one little thing you gotta be careful is, let's say if I use EIG to calculate this a at here. So MATLAB, when you see the C and the D, you let it return here, and the C matrix, okay, C matrix, okay, there are certain columns that are here, okay, certain columns, and D matrix is a diagonal matrix. D1 to Dn, right? Yeah, that's what returned from the EIG. This D1 to Dn, that represents is the eigenvalue of the matrix A. Okay, so this D1 to Dn is the eigenvalue. Each columns here is the corresponding eigenvector for each one of the eigenvalue. All right? Yeah. So. Okay, it's eigenvalue. But however, the eigenvectors that are here, they're normalized. Okay, they're normalized. So what's normalized? For example, if you have a vector 1, -1 here. Exactly. So the MATLAB giving you is 1 over √2, -1 over √2. Okay? Yeah. So in many cases, the normalized one is not an integer number. So when you try to use this eigenvector here to form the p, it might look pretty odd though, right? Yeah, not as beautiful as an integer number. So in this particular case, I would encourage you to do is try the hand calculation. Okay, hand calculating the eigenvector, and then form the p matrix, and then use the formula here to calculate a to the power of k. Okay. Okay, so give it a try. If you have any difficulties, let me know. Any questions? Okay? Yeah. So you can come here and pick up your assignments. Yeah.